In this video, we will discuss events involving AND. The multiplication rule of probability for the event A and B. If A and B are any two events, then P of A and B, the probability of A and B, is equal to the probability of A times the probability of B given A. If A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B. Since the probability of B given A is equal to the probability of B if A and B are independent events, the first rule works in all cases. For example, each year Jackie adds to her book collection a number of new publications that she believes will be of lasting value and interest. She has categorized each of her 20 new books for 2020 as hardcover or paperback and as fiction or nonfiction, as shown in the table below. If Jackie randomly chooses one of those 20 books, what is the probability that it will be A, hardcover, B, fiction, given that it is hardcover, or C, hardcover and fiction? Solutions. The probability that it's hardcover. 8 of the 20 books are hardcover books, so the probability that a hardcover book is chosen is 8 out of 20, or 2/5. Fiction, given that it's hardcover. 3 of the 8 hardcover books are fiction, so the probability of choosing a hardcover book a hardcover fiction book is 3/8. I don't know why I wrote R there, but my OCD is making me change it. Finally, the probability that the book is both hardcover and fiction. Using the formula probability of A and B equals probability of A times probability of B given A, the probability that the book is hardcover and fiction is equal to the probability that it's hardcover, which was 2/5, times the probability that it was fiction given its hardcover, which is 3/8. That's 3/20. We can also simply note from observation of the table that exactly 3 books are hardcover and fiction out of the 20. Another example. The table to the right lists the 8 planets of our solar system. Carrie must choose 2 distinct planets to cover in her astronomy report. If she selects randomly, find the probability that the first one is closer to the sun than is Mars, and the second is closer to the sun than is Saturn. So first we define the events. First, A, the first is closer than Mars, and the second is closer than Saturn. Well then, P of A is 3/8, because 3 planets, Mercury, Venus, and Earth, are closer to the sun than Mars is. If a planet is closer to the sun than Mars, then it is also closer to the sun than Saturn. So for the second part, there are only 4 planets that qualify, since the planet must be distinct and the first is one closer than Mars. That leaves 2 of Mercury, Venus, and Earth, Mars itself, and Jupiter. So the probability of B given A is 4/7. Therefore, the probability of A and B is the probability of A times the probability of B given A, which is 3/8 times 4/7, which is equal to 3/14, or about 0.214. Another example. Carrie must again select 2 planets, but this time they are for 2 different reports and they need not be distinct. Find the probability that the first is closer to the sun than Mars and the second is closer to the sun than Saturn. Solution is we define A and B as in the first problem, so the probability of A is 3/8 as before. Now, however, the same planet can be chosen for B, so the probability of B given A is equal to the probability of B, which is 5/8. Event B is independent of event A, so the probability of A and B is equal to the probability of A times the probability of B, which is 3/8 times 5/8, which is 15/64, or about 0.234. I believe we just have one more example. No, 2 more examples, sorry. In this example, a single card is drawn from a standard 52 card deck. Let B denote the event that the card is black, and let D denote the event that the card is a diamond. Are the events B and D independent? No, they're not independent. The probability of drawing a diamond with no conditions is the probability of D, which is 13 out of 52 or 1/4. Because 13 of the 52 cards are diamonds, however, because 13 of the 52 cards are diamonds. However, diamonds are red, so none of the black cards are diamonds. Therefore, the probability of D given B is 0 out of 52, or 0. Since the probability of D is not equal to the probability of D given B, B and D are not independent events. If you draw a diamond, you can't simultaneously draw a black card. That's what this comes down to. Are the events of A and B mutually exclusive? Yes. Mutually exclusive events cannot both occur for a given performance of an experiment. Since no card in the deck is both black and a diamond, B and D are mutually exclusive events. Now on to our final example. The local garage employs two mechanics, Ray and Tom. Ray does twice as many jobs as Tom, and Ray does a good job 3 out of 4 times, while Tom does a good job only 2 out of 5 times. Honestly, if he's getting less than half of his jobs good, I would fire him, but that's me. If you take your car in for repairs and you have no say as to the mechanic selected, find the probability that a good job will be done. So first we define the important events. R is that the work is done by Ray, T is the work is done by Tom, and G is that a good job is done. So Ray does twice as many jobs as Tom, so the unconditional probabilities of events R and T respectively are 2/3 and 1/3. We can easily figure out the probabilities of Ray and Tom doing good jobs based on the problem statement. The probability of Ray doing a good job is 3/4, while the probability of Tom doing a good job is 2/5. We have these probabilities. P of R is 2/3, P of T is 1/3. The probability of a good job given that Ray is the mechanic is 3/4, and the probability that of a good job given Tom is the mechanic is 2/5. The probability of good work is based on two mutually exclusive events. Ray is selected and does a good job, or Tom is selected and does a good job. So the probability of a good job is equal to the probability of R and G plus the probability of T and G. That's the probability of R times the probability of G given R, plus the probability of T times the probability of G given T. And that is 2/3 times 3/4 plus 1/3 times 2/5. And that comes out to 19/30, which is about 0.663. And that's the probability is about 63.3% that good work will be done on your car. Better than could be, but not as good as I'd want it to be.